We've been discussing chemical equilibrium, and in our previous discussion, we brought up the fact that equilibrium, in the case of chemical reaction, is the point in time in which the rate of our forward reaction has become equal to the rate of our reverse reaction. When that's the case, our concentrations become constant. There's no net change because we're forming our products as quickly as we're turning around and reforming our reactants. Now, the consequence of this is that at equilibrium, rather than having only products, we actually get a mixture of leftover reactants and products. Now, we can describe this equilibrium mixture using what's called the equilibrium constant. We're actually going to find there are many different equilibrium constants. Here we're going to be looking at what we call Kc. This equilibrium constant gives an indication of how our product concentrations relate to the reactant concentrations at equilibrium. So for example, we can look at a generic reaction, reactant A reacting with B, producing C plus D. The equilibrium constant, or the expression, is set up as follows, as the concentrations of our products raised to their coefficients divided by concentrations of reactants raised to their coefficients. So this equation here, this is referred to as an equilibrium expression. When we set that equilibrium expression up, not all species are always included. It depends on phase. If we have a pure solid or a liquid, their concentrations are understood to be 1. They are therefore omitted from our equilibrium expression, and they're from the calculation of K. So when we set these up, the only things that appear in our K expressions, or equilibrium expressions, are going to be gases or aqueous materials. So in order to be able to describe our equilibrium mixtures, we need to be able to take our chemical reactions and we need to set up those equilibrium expressions. So that equilibrium expression was a fraction. It's got a denominator and a numerator. That numerator, or the top value, will always be my products. The bottom value, or the denominator, will always be my reactants. And in our equation, those reactants and products were all raised to some power. And what those powers were coming from were the coefficients in our balanced chemical equations. Now, if we're talking about describing the equilibrium mixture, when we go to set up that equilibrium expression, what we're needing to put in there are equilibrium concentrations because it's based on those concentrations at equilibrium. We can talk about concentrations at a variety of points along our reaction. We may sometimes talk about an initial concentration. That is going to be the amount we start with before any reaction occurs. But we can also talk about equilibrium concentrations. We might see this represented with a concentration with an EQ subscript. This is going to be the amount after reaction once equilibrium is reached. Now, we said this is going to give us an indication of how our product concentrations relate to our reactant concentrations at equilibrium. If our K value is large, we're asked what would be present in the largest amounts, the reactants or products. So you think about when we're dividing things, if the value I get is large, that usually means I'm dividing by a much smaller number. And if my smaller number is my bottom number is my smaller number, my reactants, that means that my products will be present in the greater amount if I have a large K value. If that value is small, that usually means I'm dividing by a larger amount, so that would mean that my reactants are present in greater amounts. So again, we need to be able to take balanced chemical equations and write the equilibrium expressions. So we're always setting these up. It's concentration of products over reactants, each raised to their coefficient. We only include aqueous materials or gases. So when we set this K up here, it's going to be the concentration of my product, the COCl2, divided by each reactant. My reactants are both gases. And they all have coefficients of 1, so they're all raised to the power of 1. Now my next reaction, I've got N2O4 as a gas producing 2 NO2 gas. So again, it's concentration of my product raised to its coefficient divided by the concentration of my reactant raised to its coefficient. So I've got the NO2 concentration squared divided by the N2O4. Now both of these particular reactions, they were all homogeneous, they were all gases. But with C, notice I've got solids. Solids we will always omit from our expression. So when I go to set this up, it's concentration of my products, but my magnesium oxide is a solid, so we're going to omit it. My next product is the carbon dioxide as a gas, so we include it. Normally we would then divide by our reactant, but our reactant is a solid, so we omit it. So my K is just the K equals the concentration of the carbon dioxide. And then finally we've got sodium chloride breaking into sodium cations aqueous and chloride anions aqueous. My K is going to equal concentration of my products, each raised to their coefficients, divided by my reactant. My reactant again is a solid. We omit it, so there's nothing in that denominator here. Now we mentioned briefly already that we're going to encounter different K values. When K is calculated using concentration, we're going to refer to that as Kc. But if I've got a reaction of all gases, it's more common that we're probably going to measure pressure. And so we could also express our equilibrium constant in terms of pressure. And when we do that, we're going to call that a Kp, where P or Kp is going to use partial pressures of a particular reactant or product. So the difference here between a Kc and a Kp is that Kc is going to use concentrations, while Kp uses pressure. They're set up the exact same way. So no matter what type of K we're looking at, they're always set up the same. So I'm going to have the concentration for Kc, the concentration of my product, raised to its coefficient, divided by each reactant, raised to their coefficients. Kp, again, the only difference is I'm going to use pressure. So it would be the partial pressure of my product raised to its coefficient divided by the pressures of each reactant raised to their coefficients. So again, set up the exact same way. The difference is one we would plug pressure in, the other one we would plug concentration into. Now, K is a constant. It's going to be a constant for a particular reaction at a particular temperature. There are millions of chemical reactions out there. We have limited space in things like textbooks to store those constants. So one of the things we can do is we can manipulate our K values. If K is known for one reaction, we can find K, which we'll call K prime, for related reactions. And there are two types we're going to take a look at. We can either look at K for the reverse of a given reaction, or K for multiples of reactions. So, K, we told for a reverse reaction, K prime for the reverse is equal to 1 over K for the forward reaction. So, if my reaction was A plus B produces C, so my K for that reaction would be the concentration of C divided by A times B. But if I looked at my reverse reaction, and we're going to find for these reversible reactions, we're going to write them in the direction that we're interested in. So say I'm actually interested into C breaking into A and B. The K, so that's the reverse of my original reaction. K prime here, or K for this one, would be A times B over C. If we compare these two, they are inverses of one another. That's why to get K prime for a reverse reaction, we're going to take the inverse, 1 over that original K. Now we can also encounter K's for multiples of reactions. In that case, K prime will equal K to the X, where X is the multiple. So we can look, for example, we've got A plus B producing C, and we're told K is 4. 2A plus 2B produces 2C. Notice here the coefficients are 2 times the original. So this is what we mean by a multiple. The coefficients are a whole number multiple of the original reaction. So these are 2 times the original equation. So that means we're going to do K squared. So there's other manipulations that we'll see in later chapters. For right now, we're going to look at K for a reverse reaction or K for a multiple of a reaction. So looking at problem 13 here, we've got this reaction where we've got 2 COF2 producing carbon dioxide and carbon tetrafluoride. And we're given K for that reaction. K is 2.2 times 10 to the 6th. We're then asked for K for the following reaction. I've got 2 CO2 producing 2 CF2 and 4 COF2. So we're asked for K for that reaction. So what we're going to do is we're going to compare the reactions to see how they are related. So first thing I noticed comparing these two reactions is that in my given reaction, the COF2 is a reactant, but it's a product in the reaction we're interested in. So it is the reverse of my original. And if it's the reverse, K prime is 1 over the original K. But that's not the only difference that we see. In my given equation, coefficient for the COF2 is 2. Here the coefficient is 4. For all of my coefficients, the equation I'm interested in, they are double the original equation. So that means we're also dealing with a multiple of the original reaction. So if it was a multiple, we say K prime was K raised to that multiple. So we're going to need to combine these two. So our K prime is going to be 1 over K squared. And again, we're squaring it because the coefficients are double the original coefficients. So this would be 1 over 2.2 times 10 to the 6th squared. That's going to give me a K of 2.1 times 10 to the negative 13th. Now, when we look at reverses of reactions, I had a fairly large K originally. We're doing the inverse. The larger the K for that forward reaction, the smaller the K will be for that reverse reaction. Now, for a given reaction, we want to be able to set up K expressions, equilibrium expressions. We want to be able to calculate equilibrium constant values, and we want to be able to use those values to get information about our equilibrium. That's the whole point of those K values. So we're going to take a look at the significance of K. K's purpose, and we're going to see lots of K's, and they always have the same purpose. The purpose of K is to judge the extent of our reaction or process. It can be used to describe the position of the equilibrium. So that's the terminology we throw out there, is the equilibrium position. When K is large, that means products are present in greater amounts. So we kind of mentioned this conceptually already. When K is small, reactants are present in greater amounts. So when we talk about K, K can be small, intermediate, or large. And so we'll first take a look at a small K here. K is small when it is less than 10 to the negative third. When that's the case, there are mostly reactants present at equilibrium. The equilibrium is described as favoring the reactants. So if we ask about the position of the equilibrium, it favors the reactants. This occurs when the reverse rate is much faster than the forward rate initially. So we're not producing very much product, and when we do, it very rapidly turns around and reforms reactants. So we'd have a scenario where we have mostly leftover reactants at equilibrium. We have very few products being formed. And so we can see that here with this reaction of the N2 plus O2 producing 2NO. So where the two dots are connected, that's my product. We have very few product compared to leftover reactant. So lots of leftover reactant. Very few of my product being formed. So that'll be the case when K is small. And the smaller that K value, the larger that difference is going to be. That we can get to some scenarios where K is so small that essentially we are not producing measurable amounts of products. Now, if K is large, that's when K is going to be greater than 10 to the third. This will be a scenario where at equilibrium, we have mostly products being present. Very few reactants left. So when we describe the position of our equilibrium, we say that our equilibrium favors the products. It's mostly products present. This occurs when the forward rate at the beginning is much faster than the reverse rate initially. So we're able to form products very quickly, but the rate to reform reactants is slow, so we get predominantly products being formed. And so we can see that again in our image here where the products are the white and red stuck together. The reactants are the individual, so this white and this red. So I got very few of the reactants left. They're still there, but very few reactants left, mostly product being formed. The larger that K, the closer that reaction gets to completion. And then finally, we can have an intermediate K. So that's when K is between 10 to the negative third and 10 to the third. When that's the case, when we reach equilibrium, we have a significant mixture of both reactants and products at equilibrium. They're not necessarily equal, it's just that we have comparable amounts of both. So if we had reactants and products, they're going to be comparable amounts. This occurs when their initial rates are comparable, they're somewhat similar, so we're able to produce significant amounts of both. So here's where we're in that middle ground. We've got that mixture, significant, measurable, comparable amounts of reactants left, significant, measurable, comparable amounts of products formed. So looking at problem number 15, we're given a K. We're told for some particular reaction, K is 1.5 times 10 to the negative fifth. We're asked, is this a small, intermediate, or a large K? And this particular K is less than 10 to the negative third, so it is a small K. So we said when K is small, we have predominantly reactants left over at equilibrium. So if I have predominantly reactants, then my position of my equilibrium is said to favor the reactants. Which again just means we've got mostly reactants left over. We haven't used hardly any of them. We've got very few product. What this tells us about our forward reaction is that the initial rate of that forward reaction is too slow. Looking at another example with problem 15, we're told that K is 2.7 times 10 to the 8th. This is a K that is greater than 10 to the third. So that's going to make that a large K. If K is large, the equilibrium favors the products. We have predominantly products formed, very little reactant left over. This tells us that we have a fast initial rate, or faster, significantly faster than my reverse. Now, K is constant for particular reaction. We're asked if we think about how temperature impacts our rates. So that equilibrium mixture is dependent on rates. It depends on who's faster initially. Is it the forward that's faster? Is it the reverse that's faster? Or are they comparable? Remember that temperature impacts rate. So if temperature impacts rate, we're asked, does it impact K? And yes, absolutely it does. So K will be constant for a reaction at a particular temperature. So with these Ks, we need to be able to take balanced equations and write equilibrium expressions. We need to be able to manipulate Ks for related reactions. We need to be able to look at the size of a K and indicate what does that tell us about our equilibrium. What does our equilibrium look like? Is it more reactants? Is it more products? Or is it comparable values? So as we move on to other videos, we'll look at actually calculating K and using K to get information about our equilibrium.